Hello everybody, welcome back to another video. I know it's been 2 weeks, but I've been in Florida, so I've been unable to record. And I guess the first thing I want to get into is some calculus content because I posted on our Instagram that we would be doing more of this. So today we're going to be talking about the definition of a derivative, which follows the other limits video that I posted on this channel. So first off, we have this graph here. And what is a derivative? Well, a derivative, as you may know from like a verbal explanation, is the instantaneous rate of change at a point, or like the slope at a certain at a one point on the line. That is the slope. So say for example, we have this point here, then the tangent line, which is based off the slope that you get from the derivative, is pretty much would probably just be something like this, right? Now, I try to keep that as straight as possible, but since it is a tangent line, remember tangent means it will only touch the line once. This is a little inaccurate because here I have it, well, I had it touching the line a little bit. But anyways, so given that, how do you get a definition, a mathematical definition for a derivative? Or how do you calculate it, I suppose? So this is why you learn limits first, because the definition of a derivative is based in limits. You can find a derivative with a limit. So first, let me just erase that really quick. Let's talk about a secant line. So secant line will be like this, right? You have 2 points. It's the standard delta y over delta x formula. So like y2 minus y1 over x2 minus x1. And so that's how you calculate the slope for that, right? But a derivative is at 1 point. So you can't fully do that here. Now, say that we're trying to find a derivative at this point here. And well, one way that we can try to approximate it is to take the secant line using this other point here. So let's say we do that. Well, you can see that that's not very accurate. Even though my line is terrible, you could probably be able to tell that that's not very accurate, right? So how do you get it more accurate? Well, you just have to get it closer. So we had the point up here originally at around the y=4 mark, but what if we bring it like here? With such a smaller distance between the points, the line is closer to being or having the same slope as the derivative. And this is basically what you can do to calculate the derivative, because you can sort of have this point here, and then say we have another point here, and then you have the delta x between the points, which is just the change in x or difference between the x of the points, right? So if you're trying to find the derivative at this point here, then how do you think you would do that given the delta x and what we just talked about? Well, what you would try to do is bring the delta x to 0. Because if delta x equals 0, then you're at the point, and the only slope you can get is the instantaneous slope at the point. And so how do you do that given this equation? Because if delta x was 0, then the bottom, the denominator of the equation would be 0. And you can't have that because obviously that's undefined. So one way to do this is with limits. So what mathematicians came up with, the original ones who invented calculus, they came up with a limit equation for this, of course. And remember, we said that we want delta x to be 0, but you can't really technically ever get delta x to fully be 0. So what we're going to be approaching is we're going to be having delta x approach 0, because then in the limit, it'll get smaller and smaller and smaller until you get the derivative that you want. And then you're still going to have your like y2 minus y1 over here, and then over delta x. So how do you get y2 minus y1? Well, you got to think about it like this, okay? If we have a function, then to get y2, it would be the starting value, so like x, for example, and then you'd have to add the delta x. And let me switch over, well, I'll do that in a second. So you have that, right? That's your y2, and then to get y1, you just need to go from a starting point, which is just x. So you just have to subtract f of x. And this is the limit definition of a derivative. Very important to have that memorized. Will it necessarily show up on the AP Calculus tests a lot? I wouldn't say it would show up a lot. I took the test last year. I didn't see it that much. But it is important to know because this is where derivatives come from. So let me erase this and then switch over to the Drawboard application. Now, given the limit definition, and I'll rewrite it up here now, the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And sometimes, by the way, you will see delta x represented as h. So if you see like f of x plus h minus f of x over h, well, that's the same thing. So just keep that in mind. Now, let's give ourselves a function here. All right, let's give ourselves a function, the same function we were using before. Why don't we say that? So let's say f of x equals x squared. Okay. And let's say we want to find the derivative at the point where x equals, I don't know, 3, right? And we'll come back to that later. Because first, the first example I want to go through is just a general derivative. And the general derivative is this equation that we've put in the top left. And so what this will do is find you the equation for the derivative or the equation for the slope at any point. So we can use that with our function x squared to figure this out. So how do we bring this with x squared? So we would write, just let me use a different color, the limit as delta x approaches 0 of, well, f of x plus delta x in this case would be our x plus delta x squared, because you're just replacing what's inside here with the x here. And then so we're going to subtract f of x, which, keep in mind, is just x squared. And then over our delta x. This is all going to be over our delta x. So as you can see right now, this is still not solvable because the denominator is still 0, and we can't have that. It's still undefined. So let's go to step 2. The limit as delta x approaches 0. Now let's expand this out. So take a minute and think of the expansion. Okay, so when that's expanded, it will be x squared plus 2 delta x plus delta x squared minus x squared over delta x. Now, if you notice why this works already, then good job. But if you don't, that's okay. Because we can see that we have x squared minus x squared. So we can cross these out. And then that leaves us with the limit as delta x approaches 0 of 2 delta x plus delta x squared over delta x. Now, if you see why this works, then good job. Because you can see that this is just the limit as delta x approaches 0 of delta x. You can pull out a delta x. So you would have 2. Just so you know, there's supposed to be an x here. I just forgot that. So x So this will be 2x plus delta x over delta x. And now these delta x's cross out, and you can see that you're left with something where it's not going to be over 0, so it's okay. So we have the limit as delta x approaches 0 of 2x plus delta x. And so this is going to go to 0, and then you're just going to be left with 2x. So now given that we have 2x, and we have our x equals 3 from above that we want to try, what should the slope be, right? Well, if you input 3 for x, you should get 6. So for f of x equals x squared, you would get, for the slope at x equals 3, 6, right? So let's try one more example problem then. So let's try f of x equals x cubed. Okay, so we are taking the limit as delta x approaches 0 of x plus, well, I'm going to use h in this actually, just to show that it can be either h or delta x. So x plus h cubed minus x cubed over h. So this will go, well, I'll give you guys a minute to figure out how to solve this. Okay, so coming back to that, let's see if you guys are right. So we expand the first term. So we get x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed over h. And these first 4 terms here are just the expansion of the x plus h cubed. So we can see that this x cubed crosses out with this x cubed, leaving us with the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed over h. And what do all these terms have in common that results in the same type of answer as the last one? They all have an h. So we can pull out an h. So let's do that. The limit as h approaches 0 of h times 3x squared plus 3xh plus h squared over h. Now these h's will cancel out, and then we will be left with the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Now when h goes to 0, these will go out because this will be multiplying by 0, and then this will be gone. So we're left with 3x squared. So say you were taking the slope at the point where x equals 2, then you would have 3 times 2 squared, which is just 3 times 4, which is 12. And that is going to be it for this video. If you guys found this useful, please feel free to like, subscribe, and comment. Otherwise, there will be a following video on easier ways to find derivatives. And thank you guys.